Hi calculus students, welcome to Snow Day 101 and day 2 of our area between curves. There are homework solutions here. I'm not going to spend too much time on those with the exception of 22, which was particularly challenging. But I do want to go through some things we didn't get to touch on in class. We did not talk about what do you do if there's no distinct top curve and bottom curve. Like in the picture here, there's a distinct right-hand curve and left-hand curve, but not a distinct top and bottom. Also note that these two curves are, the functions are given in terms of y. They're not really functions, the equations. And so my guess is we're probably going to have to think about area with respect to the y-axis instead of x. So everybody tip your heads to the right. No, really, tip your head to the right. If we're looking at, oops, come back here. If we're looking at this particular curve, which is this one, the area between that curve and the y-axis would look like this if I shade it all in. Does that make sense? If you keep your head tipped to the right and we look at the other curve, this curve in red, this is x equals y squared, the area between that curve and the y-axis is here. We only want the part that is in yellow there, and we notice that it's blue with no overlapping red. We don't want any of the red. How do we get rid of the red? So when we find our area, when we do our integral, we're going to be taking our blue curve, finding its area, and subtracting the area for our red curve. Keep in mind that you can write integrals that were differences as a single integral of a difference. The way I found these two bounds was by doing something similar to what you would do if these were equations in terms of x. I set them equal to each other, and I solved for y. Notice that we're going to end up with a quadratic equation. We end up with 2y squared minus 2y minus 3 equals 0 if you move everything to the left-hand side. To solve that, use your quadratic formula, and the two answers that you get for your, what normally you get as x, will be your y values of those points of intersection. Since we're integrating with respect to y, our bounds also need to be with respect to y. Similarly to how we find our bounds when we're finding area under curves on the x-axis, we usually start with the left-hand side and move to the right, so our integral would be from a to b. A is smaller than b. Look back at this graph, tip your head to the right. We're going to take the smaller y value first, and then have our, the smaller y value first, and then to our bigger y value. So that's why the integral goes from negative 0.823 to 1.823. Again, for y, if you're integrating and you're trying to get the area that's between your curve and the y-axis, you're looking at an integral that starts low and goes high. So from a to b. Otherwise, finding the area is very similar. Again, the other difference is that we have the right-hand area minus the left-hand area rather than top minus bottom. Turning your head to the right might really help you. Just keep in mind, though, we're not going left to right when you tip your head to the right, but small y value to bigger y value for our bounds. So here's one to practice. I've given you two functions here in terms, one in terms of y, the other in terms of x. When you graph them, they look like this. One is linear, the other a parabola. Go ahead and try to set up the area expression for these. Press pause, and the solution is forthcoming. So once I had my graph, I really decided I need these points of intersection so that I can have my bounds for my integral. I'm looking for y values. So I took my equation for the line and rewrote it in terms of y, set it equal to my equation for the parabola. I got a quadratic equation. Again, I used quadratic formula and I solved to find my y values, which are now my bounds. Again, small y to big Y. Since my linear equation is to the right, I took my right-hand equation and subtracted my left-hand equation. If you're still having trouble, tip your head to the right, which equation looks on top. That right-hand equation is what is going to look like it's on top if you tip your head to the right. Because the hard part of these problems is to actually set up the area expression, you feel free to use your calculator to go ahead and then integrate. For some homework solutions, I'm going to gloss over these fairly briefly. Feel free to pause and look at them in length or in depth. 22 is where I want to spend the bulk of my time here. Number 1, I looked for a top and a bottom curve, and I set up my integral as top minus the bottom, using the bounds where they intersect. Very similar for number 4, except I have to tip my head to the right, and my bounds are now y values instead of x values. And my top curve, so to speak, is the right-hand curve here, and my bottom curve is the left-hand curve. So right minus left. Don't forget to distribute your negative sign or use parentheses appropriately. 7 is very similar to number 1. This one, however, I had to graph my own. They said something about a rectangle that approximates the area. What you could do is the only rectangle you could make here would be a really hideous approximation with a length of 1 and a width of 1, and we'd have a horrible approximation of area of 1. I'm less interested in you being able to do that than I am in you being able to set up the integral for the area and solve either by hand or calculator. Number 7 through 13 maybe, those are fairly nice to do by hand, but again, the focus is on setting up the area. Feel free to use your calculator for integrating. So in 7, the line is on top, that's why we have the linear equation minus the quadratic equation. Here, I don't have a distinct top and bottom in number 11, so I'll be looking for a right-hand curve and a left-hand curve. In order to find the points of intersection, I rewrote my linear equation and set it equal to my quadratic, and I actually factored this one. It factors nicely, and I found my bounds. Make sure you have smaller y value to bigger y value as your bounds, and don't forget, if you have to distribute your negative. That wasn't a problem in this case. Number 13, very similar to what we just saw in number 11. We don't have a distinct top and bottom, but we do have a distinct right and left. Or if you tip your head, they do look like top and bottom. Be careful with your bounds. Those can be found by solving an equation. When you set the two functions equal to each other, I get y equals plus or minus 2. I don't have to distribute a negative sign, and I use my calculator to solve. Number 16 is a bit of a challenge. Finding the integral of an absolute value is easier to do if you split it up into two distinct pieces. If I call this side y equals negative x, and I call this side y equals x, I can find two separate areas here and here using two separate integrals. I don't have to actually use two separate integrals, because if we notice, we have symmetry for both graphs. So the area in red here on the left is going to be exactly the same as the area here in blue. So I did set up originally two integrals that I'm going to add together to get an accumulated total area, or I could make a single integral just for the left hand or just for the right hand side because we have symmetry. Your choice. You will end up with 26/6 or 13/3. This next one, the graph was really icky when I first graphed it. I have my y equals x to the 4th here, and then my squiggly red graph is x times sine x squared, particularly ugly. It's hard to see how many times they intersect, so I, at first, when I graphed it, zoomed way out, like this picture, so I could see, does it look like they intersect more than once or not? They actually look like they intersect twice or 3 times, so I zoomed in, and I saw one intersection here and one here. It looks like there might have been one here, but when I zoomed in, I see, nope, no intersection there. So I only have 2 intersections. And I solved for those by calculator. It asks you to approximate. Approximate in this case means you're not going to get an exact value for x sine x squared. You're going to get an approximation anyway, so that's all they're looking for. I found my bounds at 0 and 0.9. Those are the two intersection points. Those are the x coordinates, because we're doing this in terms of x. I do have a distinct top curve and bottom curve. I set up my integral. When I put this into my fancy calculator like Max has, it did not give me a decimal answer. It gave me an expression. So I went and integrated this by hand, and I get 0.037, or approximately 0.04. On the AP, do remember, they're going to ask for 3 decimal places, so the first answer is probably a little bit better for the AP. On to 22, which might have been a little confusing. They gave you 2 graphs. They said 2 cars start right next to each other, and they accelerate. They wanted to know who is ahead after 1 minute. So here's 1 minute. That's where the 2 curves intersect. This is a velocity curve. The area under a velocity curve represents what? No, really, I'm asking. Area under a velocity curve represents distance traveled. If I set up my velocity curve to start at 0 and continue for a while for my velocity function with respect to time, this function, remember, is called the accumulation of area function, and that's what they're asking us about. What happens as time ticks on, how much distance, or area under velocity, has been accumulated. For car A, my area is approximately this purple triangle-y thing. But for car B, between 0 and 1, my area is only this much. So if my purpley area was bigger than my green area, who traveled further? Car A traveled further. That's what they ask in part A. So car A traveled further between time 0 and 1. So this is greater for car A than it is for car B. They then ask, what is the meaning of the area of the shaded region? Well, if we looked at it before when I shaded in the purple part is the distance that car A traveled. The little green part is the distance that car B traveled. So what's the area in between? Go ahead, really answer. That area in between here, that's the difference in their area. That's how much further car A traveled than car B. They asked in part C which car is ahead after 2 minutes. So after 2 minutes, now I'm looking at an accumulation of area from 0 to 2. Let's look at the accumulation of area for car A. I'm going to put that in black here. That's all of this area. Okay? Now I'm going to look at the accumulation of area for car B from 0 to 2. That's this area. Whose area was bigger? The black area or the yellow? Black actually is bigger. You can do some approximation using the grid they gave you, and you can add up how many squares are in this overlap versus how many squares are in the original overlap. And it looks like the original overlap is greater, which means car A is ahead more, or still ahead, has created greater distance than car B. They then ask, and this was a clue in part C actually, in part D they say estimate the time at which the cars are again side by side. So I know that they haven't been side by side since 0, and my guess is that since they asked me in part C about who's ahead at 2, they still haven't been side by side, but that's just a guess based on the wording. So when is car B ahead? Well, what I did for this was I looked at the graph and I said, okay, here's car A and here's car B. I want to know when the area between car B and A, up here, that difference, is greater than the difference here. So all I did was approximate using blocks on the grid to determine that at about 2.25 minutes, it looks like car B finally overtakes car A, because the difference in their areas all of a sudden tips in B's favor. I hope that made some sense. Tonight's homework is still on area between curves, very similar problems, more applications, and I will see you on Tuesday with homework to discuss area. Thank you.